Alright, here goes nothing. Let's get this started. So, as we have been saying, we are about 75% or something, and this is my map of what has been implemented and what is not. So I am trying to convince myself if we should follow the same order, or we go for the easier ones first. But let's just continue. So next one will be LSR. Zoop. LSR. So it's logical shift right. Let's dock. Okay, sorry for interruption. So logical shift right, it changes A, C, Z, N, and A is equal, divides itself by 2, or what is the same, it shifts the binary number 1 bit to the right. So each of the bits of A in F or M is shifted 1 place to the right. The bit that was in a bit 0 is shifted into the carry flag. Bit 7 is set to 0. Okay, so here we go. 0 flag is set if result is 0. Carry flag set to whatever was the 1. And negative flag is set if bit 7 of the result is set. I don't think that can happen. Anyway. I am not sure about this, but maybe it looks at the bit 7 instead of the bit 8, or maybe it starts counting. Oh, it starts counting on 0. Okay, that's okay. Then it is impossible to be a 1 if I am not crazy. But a negative divided by 2 should still be a negative, so I don't know how that should work, but for now let's make it work and we make questions later. So for sake of ordering, let's put it after LDY, and we want our nested view. Let's search LDY. And it's here between LDY and set A. Oh, so it says, I don't know. LSR. We have inconsistency here. We have the spaces in here and not the spaces in here. Let's fix that. I am that kind of maniac. Let's duplicate a line. This full white and start changing. This is LSR. No opcode yet. No function yet. And let's see, what do we have? So we have immediate addressing mode, 0 page X, absolute and absolute X. Wait, I am looking at LDY. Sorry. So we have accumulator. We have 0 page X, absolute and absolute X. So we did not, before we did not have an accumulator addressing mode. So what I think should happen is we will have two functions, one for register and one for memory. So let's have it logical shift right. I accidentally forgot to finish with this. Okay, here we go. Logical shift right register, and we pass a register. And LSR takes 1 byte and 2 cycles for this variant, and opcode A4, sorry, 4A. I am a little clumsy today. And the next one will be logical shift right memory. This one does not take a register, it only takes memory addressing. So we have 0 page. Let's duplicate some lines. 0 page X, absolute and absolute X. And those are 4, 6, 5, 6, 4E, 5E. This is 2 bytes, 5 cycles. This is 2 bytes, 6 cycles. This is 3 bytes, 6 cycles, and this is 3 bytes, 7 cycles. So now we have to write the functions, right? Copy, and let's search logical shift right. Where is my roar? LSR, sorry, LSL, no, we don't have LSL. Where is my shift method? Arithmetic shift place. So let's put it next to this one. So for ASL we also created one for the register and one for memory, but we did not name it memory. Maybe we should. Memory. Okay, done. So this is logical shift right. This is 2 functions. This one taking a register, and second one taking an addressing mode. Pass. So now we can start working on it. Let's take this function as a template because it's doing a shift left instead of shift right. So it takes the value from the register, it makes a copy that is shifted but in the opposite direction, and we need to first set the carry flag flag.carry equals value and 1 because it's the first bit. We can make it text to make it more obvious. Oh, and this is dot value. And okay, so it makes the shift to the right, and we don't need to make this this masking because it will never be it will never overflow, or better said, will never underflow. So p register value equals shifted. We have to update this flag. No, because we set it manually before, and we have to update 0 and negative flag using shifted, and that looks about right. Now let's do the same for the logical shift for the memory. So we will take the addressing with the addressing mode, we'll take the value, we will shift it to the right, no need for the masking on the result. So we want to set the carry flag from the previous value. Just whatever was stored in the first bit before shifting is what is set to the carry flag. We shift it, and we now store the value back to our memory map. We don't need to update the C flag, we already did it in here, and we want to update 0 and negative flag here. Okay. Okay, so in theory, this should be all. Famous last words. So, can we compromise that this is all work and done? What did I do wrong here? Oh, this is uppercase X. Okay. Okay, awesome. So now we need to create our testing function. LSR comes after LDY. So I will create a new node and name it LSR. We'll create a new script for it. Call it LSR in lowercase, and we'll use my test. So this is the first time I do it from here, and seems like it works. Aha, it should go to the NES folder. Okay, good to know. So we need to rename this to lowercase, and the same to be this one does not have immediate, it has accumulator instead. Okay. So I think we can change to full screen. The name of this function is logical shift right. Let's start changing. Oops, I did a mistake, and that is I also need to set the name in here in the function. Let's go and it is logical shift right. Let's start removing the variants that we don't need. We have zero page, we have zero page X, we have absolute X, but we don't have absolute Y or indirect. So we remove the last three ones, and we are kinda ready to start filling this up. Oh, I am making the mistake again. This is the one I should have been looking, but it was the right set anyway. So accumulator is A4, sorry, 4A. Zero page, it is 4.6. Zero page X, it is 5.6. Absolute, it is 4E. And absolute X, 5E. Okay, change the print, and we are ready to start creating the test. This is just a boilerplate. So for the accumulator, we will not need the memory part, but we will need it for the next one, so I will just copy it. For the accumulator, we have to load something into the accumulator. So I guess we have to test a couple of flags. So the best way to do that is just use binaries. So first case is we want to shift a 1. If we shift a 1, the result will be a 0. So we load into the register a 1 and we shift it, and let's see what is the result. So the result to this should be 0 in the register A. Flag 0 should be true because it's a 0. Flag negative should be false because it's not negative. We don't need overflow, and carry should be a 1 because it should be true because it used to be a 1. So let's give it a shot. Let's comment this for now. And let's see if it passes or not. So LSR accumulator logical shift right passed. So yes, it worked as we expected. So let's make a couple more cases. We don't need this memory. So we got a case where 0 was true and the overflow was false. Let's try this other case. So I will copy this, and in theory this byte should be gone and a 0 should be added. So this is non-negative, this is non-zero, and the carry flag is also false because we did not have a 1 in the previous. So let's give it a shot. Okay, it worked. So I think this is the only 2 cases we need, because the negative flag is impossible to be set. It will always be false, because here say bit 7 is set to 0, so it will never be a 1 into bit 7. So this is our hope. This is what we want to move to the next area. So I will copy this and paste it in here, and I will uncomment this because now we want to work with 0 page. So instead of loading A, we are going to load it into memory, and we don't need loading into A anymore. I will duplicate this line. No, wait. I will make use of the next memory. Okay. So, and I don't need to load A anymore. So this instruction is 46 instead of 4A. And this one takes a second byte for the argument, and that is the memory address that we want to use. For the first case is 3, for the second case is 4, and that should be all. Famous last word. Let's give it a shot. This one failed, and that is because I am checking the register instead of the memory. So what I need to do is memory, and passing the memory I want to check. Okay, fixing the test. And it passed now. So we have logical shift right 0 page, and it passed. Okay, next is 0 page X. So it takes the 0 page and it adds the value of X. So let's do a plus 5. So before first let's change what is the instruction. before I forget. And let's change what is the memory that is being read in the test, +5. And before making the shifty, let's load something into X, so it can be it can move the page. So we don't no longer need to use the transfer because now we have load X. And load X immediate is A2. So we can use OXA2 to load the value of 5 into register X. That should be all in theory. And we are writing the memory in 3+5, in 4+5, and we are loading 5 into X and shifting 3+5 to the right, and then checking the memory and see if it matches our expectations. Let's give it a shot. Still page X passed. Awesome. Let's copy this or this one, because next one is absolute and it is more or less the same, except it uses a 2-byte memory address. Let's change the instruction before I forget. And now we have to change the memory that is going to be read. So this is 4003 and 4004. And because this is little endian, we have to pass first the less significant byte and after the most significant byte. And I think that is all. Try. Seems to have passed. Absolute logical shift passed. Okay. So now the only missing one is absolute X, which we make the same as before. We have to add something to the memory address, and we have to load that something into the X register before executing. So I will copy that instruction and paste it here and change the print and give it a shot. And it failed. Why it failed? Right. Oh, because I forgot to change the instruction. That's why. See, it is important. Okay. Absolute X. Logical shift right passed. Where is my music? Here it is. Hey, Cricket! Can't watch but wanted to cheer you on. What's the progress like? So this is the progress. These are the instructions, the green ones are the instructions that we have finished, and we have just also finished logical shift right. So we have one more to the list, and this is more or less the overall progress. We are about 75 or something %. So when the stream ends, I think we will be by 85%, something like that. I hope. So I thought that I was going to get a sound when the message came, but I didn't hear it. Excellent work. Thank you, Cricket. So it's nice to have you around. Oops, wrong window. Here we... this window? Yes, this window. Okay, so we are done with logical shift right. Barking, barking, barking. Woof, woof. So I forgot to create a ticket for this. So let's do that fast. And it's 32. And let's make a commit. Open bash. Status. What did we change? We added... what changed in here? Oh, okay, I renamed this function for underscore memory. Okay, so that is correct. And we added some spaces, we added logical shift right. Opcodes are correct. Bytes are correct. Cycles are correct. Functions and beans are correct. I renamed this function. I created this function. Okay, I added one script. Load the script. Added a node. This seems correct. And git add, and we add the new file. Git commit. Implement and create unit test for logical shift right. Git push. Oh wait. Git commit amend. Come on here. Closes, and which one is this? This is 32. Okay. Git push origin main. And this should be gone forever. Yay, it's done. So next is the no op. The no op is the easier one of all, maybe. Convert to issue. And let's see what is the no operation like. The no operation instruction causes no changes to the processor other than normal incrementing the program counter to the next instruction. Processor status after use, no affected. Addressing mode does not take any addressing mode, and opcode is EA and takes 1 byte and 2 cycles. So this is very simple one, and let's add it after lstart. No operation. Let's copy it, and this is a loop. And minimize. Opcode is EA. It takes 1 byte, 2 cycles. and the function is no operation. It's the most simple function at all. So let's create loop, func, no operation, pass. That's all. It passes. So the way that no op is used is that sometimes you need to wait a couple of cycles in order for the memories related to the input to update or something like that. And so they use that to keep the no op to keep the other parts in the hardware some time to update the memory before trying to read it. So the NES is kind of multi-thread, for saying it some way, because each of the chips works independently without knowing what the other is doing, but they need to not collide trying to read or write the same memory at the same time. So that is what the no op is used at sometimes, as far as I know. So let's create the no op test. I don't think we need it, to be honest. I feel kinda bad only for creating it, but let's see what can we do with it. Nope. Let's create a script and let's save it into NES test. Nope. Create. And we don't have any addressing mode. We should have a nope. No operation. And the opcode is EA. So Electronic Arts is a no operation. That is what I take from this. Func space pass, and I will just copy this print. Here is my note. And let's copy some initialization from here. And let's see what can we test. I think we can load some values and put some nodes in the middle. So let's say we have a couple of no operations in middle, and we should test exactly the same case that we tested, because nothing should happen in the middle, so it should not affect the result of this. So if this passes, then I am happy. It should not interrupt the execution, right? So let's give it a shot. So no operation passes, and that's enough for me. Okay, awesome. Git status, git add part. We added the node registration, created a function that is empty, added the test, and add the file. git commit. So what is this? Is 33. So implement and create unit test for noob closes 33. And we are ready to move on to Aura. Let's convert it to an issue, put it in progress. Oh, and of course git push origin main. Sometimes I forget. So no is done. Do. Next one is Aura, which is an OR with accumulator, I think. Logical inclusive OR. So it's accumulator or memory. An inclusive OR is performed bit by bit on the accumulator. Content using the content of a byte of memory. So zero flag is set if A is 0. So it makes an OR between the accumulator and the memory, and the result is stored into the accumulator. Okay, and zero flag is set if A, the result, is set to 0. And negative is set, so it affects 0 and negative, and not much after that. Okay, so it can be immediate, so memory is memory or immediate, and it has all the variants of the addressing mode. So let's start writing it up. Close this view and let's find our NES CPU register or A, open space. Let's take a duplicate from one of these that has the two bins. Let's remove opcode. Instruction is OR A. We will change cycles and bytes later. And instruction is inclusive or with register. So it takes a register and takes an addressing mode. Let's make some copies of this line and start filling it up. So first one is immediate, 0 page, 0x, absolute, absolute x, absolute y, I will hide these to get some more space. Okay. Indirect x, not indirect alone, indirect x and indirect y. And these two are unneeded. And let's start filling this up. So immediate is 09. Zero page is 05. 0x is 15. Absolute OD. Absolute x 1D. Absolute y 19. Indirect x 01 and indirect y 11. Okay, awesome. And let's fix the bytes and cycles. So first one, 2 bytes, 2 cycles, 2 bytes, 3 cycles, 2 bytes, 4 cycles, 2 bytes, 4 cycles. Wait, sorry, 3 bytes, 4 cycles for absolute. 3 bytes, 4 cycles, 3 bytes, 4 cycles, index y, 2 bytes, 6 cycles, and 2 bytes, 5 cycles. Okay. Now we have to create the function. This is or a func inclusive or with register. Arguments are a register and addressing mode. So let's copy some boilerplate. Let's take address and value from the address. And our result is going to be equal to b register value or value. The result is stored into the register b register dot value equals or result, and we update 0 and negative with or result. And I think that's all. So now the favorite part of everyone, creating unit tests. Yay! Let's create a node. This is called or a. Let's create a script for it. Here, or a. And this will be lowercase, this is lowercase, and all of this is lowercase. And let's change the name of this function to give a descriptive name the end, and we name it logical inclusive or. Okay, let's fold this and let's start filling the opcodes. So first one, immediate is 09, 0 page is 05, 0 page X 15, and absolute OT, absolute X 1D, absolute Y 19, indirect X is 01 and indirect Y 11. Okay, so we have a full boilerplate for this script, and we can start creating. So I will copy the boilerplate for the next instruction and comment it for now. It's just to not lose it, because I will delete the memory part from here. We don't need memory for immediate. So we are going to make an OR operation with the accumulator. So let's load to the accumulator a binary number that is easy to see. So 1 1 0 1 1 1 2 3 4 7. Okay, one more, and let's make an OR operation. 0x09 is listed in here with another binary number. We will change it in a moment. So we have to check the register A as the result. We have to check the 0 and negative flag, but not override and carry. So the first case I want to check is an OR condition that returns a 0. So let's flip it. One way to do that is put in a complement in here. Where is I'm trying to find where is the symbol in this keyboard. This works? No, of course not. Well, I will just flip it manually. So this is 0 0 1 0 0 1 1 0. So this OR, this OR will be actually a full 1 FF, but it's a good case, I guess. This is not 0, this is negative. And let's make the other case where we load something and then we make a comparison with a 0, and this one should be indeed a 0 and not negative. And we need one more that is negative, I guess. Wait, no, this is already negative, so it's fine. So let's try it. And this assertion failed. And why is that? What is the value in the accumulator? Register A 217. And why is that? Oh, because it's an OR, not an AND. So in order to be 0, both need to be 0. Okay. Okay, and now it passes. So I guess this is all the test. And we have to rewrite it for the other addressing modes. So let's copy this and replace this part and uncomment this part. So we are going to need this, and we are going to need this. So we are going to use zero page addressing to make the next test. Let's change before anything else what is the instruction. And this instruction takes the address instead of the value. So this value is the address 3, which will store this value, and this is address 4, which will store this value, and this should be O in theory. Yes, I need to change the print. Let's give it a run. We have logically inclusive zero page. Awesome. So let's move fast, and let's do the zero page X. So whatever is this value, it adds some other value, and let's change the instruction, and we need to load something into register X. So we can use load X, which is A2. I will copy this and go back to our OR, and we will load into register X a 5. And now this should be all. We load a 5 into register X, we load something into the accumulator, and then we perform the OR with the memory 3 or 4 plus the register X, and we should have exactly the same result. Give it a shot, and it works. Okay, next is absolute Y, right? No, next is absolute. There is no zero page Y? No, there is no zero page Y. Okay, my bad. So next is absolute. So let's copy this example and put the absolute here. But now we are taking a 2 bytes memory. And let's change the instruction that we are using. And let's put, it worked because it works, but I forgot to put one of the values here as well. And now that we have this value, we need to pass the 2 bytes for the memory address. This is little endian, so we put first the less significant byte and after the most significant byte. And this should already be working, famous last word. Give it a shot. And we have absolute logical inclusive OR. Awesome. So next is absolute X. So let's make an absolute plus whatever value we store in X. Let's store a value of, I don't know, F1, and make sure it works. So let's take from this example the loading of a 5, and paste it in here, and let's load an OXF1 instead. Okay, I'm using lowercase for this, so I should try to keep being consistent. And let's change the instruction 1D, change the print, and this should be passing famous last words. Okay, ahora absolute x passed. And next is absolute y instead. So let's make exactly the same test, but we are going to load into y, and load y is instruction AO. Let's go back and let's use AO instead, and let's change our instruction, and let's change this for some different value. Let's say EI, change the print, give it a shot, and absolute x wait. I am looking at the wrong print. Absolute y logical inclusive or passed. Okay, now indirect x and indirect y. These are more difficult ones, so let's take it easy. So we have 3, 4, 5, and 6. So now it will take, it will read the address from the 0 page, and then we'll go to that value in memory to find what is the value that needs to be compared. So let's start by changing the instruction, and this takes only 1 byte, and it will take that byte and the next one. So for the first one we will use 3, and for the next one we will use 5, because 3 and 4 are used together and 5 and 6 are used together. So 3 and 4 are going to point to this memory, and because this is little endianness, we have to put 03, 40, first the less significant, then the more significant, and this will be 04, less significant, and 40, most significant. Wait a second. We also want to add, indirect x was added to the 0 page or was added to the memory? I think it was added to the 0 page. So the 0 page, oops, we can make a +5, and then we load into the X register and OX05. And if I am not crazy, this should work. famous password. Let's change the print. Seems to have worked. So we have indirect X working. So indirect X worked, and indirect Y, instead of adding to the 0 page, it adds to the final memory. So instead of loading into X register, we load into the Y register, A0. We load a 5, and it will. Let's change the instruction, and it will take 3, find the memory address, and then add 5 to get the byte to make the comparison. And we change the print and give it a shot. So, or A indirect Y passes. So awesome. We have finished it. Wow. It A registered or A with addressing mode, with cycles and bytes, with opcode, created the function, added the test, and let's add this test script and commit it. Let's find what was it was 34 implemented and created unit test for A. Closes 34. Git push origin main, and this is run. Next is PHA. I have no idea what is this. Oh, push accumulator. Pushes a copy of the accumulator into the stack. Does not affect any of the flags. So push accumulator and push processor, pull accumulator and pull processor. Can we do all of them at the same time? Because they only have none of them has addressing mode. Maybe we can make them together. So yes, let's do that. Scripts. Let's find our CPU. And let's say push accumulator, push P flags. And let's add our documentation, the corner, and Godot in here, PHA, PHP, func, push register to stack. Let's gain some space, and this one only takes the register. And let's go stack push 8 p register dot value, and this should be all. Famous last word does not take anything else. Push processor status flag. Yeah, no, does not affect any flag. This is all. Now we want to also pull accumulator and pull the flag. So let's rename it to pull register from stack, and register value will be equal to stack pop 8. So let me see if pull changes the values. Yes. So in the case of the accumulator, the flags are set. In the case of the status, they are not changed, they are just red. So let's do this. If p register is not equal to flag, let me confirm that this flag is the next register flag. Register flag. Where is register flag? Okay, it takes an integer value. Okay, it looks correct. Flags.value. No, wait, it's not value. So if p register is not flag, we are going to update the 0 and negative flag with p register.value. So we can just reuse the same two functions for the accumulator and for the flag. So let's copy the function name. And let's copy only one of them. And let's go to where we want to register then, which is after or a php. No, it's not phe, pha first. And this is push. Let's duplicate one line. pha is 48. pha, it takes 1 byte and 3 cycles. Function is push register. This is to stack, and it takes a register and no addressing mode. And this is O for phi. Next is php. php. Opcode is 08. 1 byte, 3 cycles, push register to stack, and we are going to push the flag. Next is pull A, and we are going to use opcode 68 PLA. It takes 1 byte, 4 cycles, and this one is pull register from stack, and we pass the register A. And finally pull P, opcode is 28, 1 byte, 4 cycles, and we pull register from stack with the register flag. So we are done with the implementation. Now we only need test. Favorite part of everyone. So let's make it. Oh wait, I have to rename this to PLP. Let's make do we make only one file for everything? I kind of don't want to do that. So let's make one for each, I guess. So it's PHA, PHP, PLA, PLP, and let's start creating script. Let's save it into NES PHA, and none of these exist. None of these exist. Lowercase. So we just have to load something and push it into the stack. So PHA, let's go back, is 48. So let's load a 5 and let's push it. OX48. And we now assert CPU pull stack pull stack pop 8 equals 0x05. So we should be able to actually, I have an idea. Let's do this. Let's push two different values. So we load a 5, push it. We load a 75 0x75 and push it. And now when we pop them in inverted order. So we first pop the 75 and then we pop the 05. This is not immediate. This is push accumulator. This goes in uppercase. Why was it in lowercase? Is my template in lowercase or something? Let's find out. File open. Okay. Does not show the folder because it's ignored, so I will have to open it from here. Ba-ba-bum. Well, no, it is uppercase. Oh, I know what happened. So I came here and pressed Shift F5 to make it lowercase because of the uppercase in the PHA class. Okay, so that's what happened. Anyway, so this should be all. Famous last word. And it seems to have passed. PHA push accumulator passed. Awesome. So now let's copy this as is. And actually let's duplicate the script instead. So in file system, let's duplicate it and let's make it push processor, and let's start changing it. So this is push processor, push processor. The opcode is 0x0008. Now that we are working with the processor, we need to do some stuff different. Let's first change what is the opcode in our script, and we are still going to load values, but we are going to load values and try to consider what is the processor for each case. So this is load, and let's use a binary number. So this is a 0, this will be a negative, and before this we can, or no, after this we can call set flag. So where is setting the flag? What was the instruction for setting flag? It was PP clear C. Okay, set A, set store A, store X. What was the instruction for setting the flag? It was SE. I think it is this one. Carry, decimal, interrupt. But where is the version for the order flag? These are branch. Right. Branch. So this is clear, CL is clear, and SE is set, right? Let's confirm that. So CL is clear carry, and SA is set carry flag. So we can set carry after loading A, so we use an 38 to set the carry flag. OX38. So with all of this, processor should be equal 1, 2, 3, 4, 5, 6, 7, 8. So the 0 flag is true. Let's check which flag is which in our CPU. So 0 flag is the bit 1. Negative flag is false. Carry flag is true. And carry is the first flag, the first bit. So this one is true. The CPU interrupt flag, we could set it. Decimal flag, bit flag, overflow flag, negative flag. So this should be the value that we are setting. And for this case, we are going to load this value, and this value is going to change negative and 0 flag. And we can also set the interrupt flag. So set interrupt flag, let's find it in here, is 78. OX78. And for, wait, this should happen before pushing. This also should happen before pushing. Okay, awesome. And with this, T should be equal. Copy this. So we have set interrupt. Interrupt. CPU interrupt is the byte 2. So this one is set. 0 is the byte 1 is unset because we loaded this value. Negative flag was set because we loaded a negative value, a negative bit 7. Negative is set, and we did not change the carry flag, so it maintains. So I think this should be the two values. So we are pushing this, and then when we pop them in reverse order. So let's give it a shot. It seems to have passed, but I forgot to change the print. Wait, we never assigned the script, so it didn't run. Okay, we did something wrong. Cannot convert argument 1 from callable to object. So we did something wrong when registering the function. Where is our function? So push to register, push register to stack, pull register from stack. These are objects, they are not callback. So what am I doing wrong? Let's take a closer look to the call stack. Push register to stack callable. So the opcode, let's see what is the instruction, is PHP. Code is 8. Is that correct? I think yes. PHP code is 08. Okay. And the callback is a callable, but we don't know what is inside the callable. But it seems to believe flag is a callback. Flag should be this register. There is another flag, shadowing or something. Oh, I see what is the problem. So this function push register takes a register 8-bit, but flags is not a register 8-bit, it's a register flag. So let's just say variant. A comment. The register can be register 8 bits or how is this class called? NES register flags. But now we call it a variant. And let's move it up. Variant. Let's try again. It seems to have passed now. So push processor passed. So we have testing for push and pull. Sorry, for push alone. And theoretically we also made the pull. but no, we did not do the pull because we only know that it is pushing the right value. We now have to test that it is pulling the right value. So pull accumulator. Let's take push accumulator and duplicate it. And assign it. And this is and let's start renaming stuff. This is pull accumulator. Pull accumulator. Opcode is let's find pull accumulator. Opcode is 68. Okay, and now we want to do something with this, right? So let's load a 5. Let's push it. Let's load something else. Yes, let's load a 75 and now let's pull it with a 68. So we have nothing in the stack to pop. Instead, we have to test that the register A is equal to the 5 that we originally pushed. So we load a 5, push it, load a 75 and pull everything to 75. And actually we could make a negative value. So we can make an F5. And that will be a negative value. And we can now assert, because this also updates the 0 and negative flags, CPU flag negative value equals true and 0 equals false. And wait, so yes, this is correct. Did we assign the script? No, we did not. No, yes, we did. So we can give it a shot. And it says full accumulator passed. So it did our expectations. So finally, let's duplicate PHP with name PLP. And let's rename some stuff. No opcode. This is PLP. Full processor. And let's remove the assertions. And let's see what is the code is 28. So let's do something on. Let's push something to the processor. Then let's change it and then let's pull it. So this is what we want to change. So we push this value and we have these instructions. So we have no negative, we have 0, we have carry that we set, and we can, no, let's not change that. So we push it and we load this other number and set the interrupt flag, and we have this, but let's pull it instead. And now let's assert that CPU.flag.value equals to the first one, the one that we pushed and then pulled it. And this should be all for the test. Is it? And seems to have passed. Oh, I forgot to change the print. Yes, full processor passed. So we got all 4 of them. Awesome. Adding part, register it, the code, create the functions, added the test, and add the script for the test files. And now let's commit it. So let's see what can we do with this. So let's delete these 3. And let's edit this one. PHL, PHP, PLA, PLP. And okay. So this is 35 now. So this is implementation and unit test for PHA, PHP, PLA, and PLP. Closes 35. Git push. This should be gone. Awesome. Let's see. So that gets rid of 1, 2, 3, 4 stuff in our table. Okay, I think this is all for today. It was awesome progress. We have, let's say these 3 are these 3, so that means we are about 85% complete. So that is awesome progress. We are about 85%. It would be like there. Yes, I think so. So thank you very much for watching, and see you every Wednesday and Saturday continuing with this project, and have a nice time.